Howdy! The purpose of this video is to talk about the effect of doping metals and semiconductors on their electrical conductivity. So when I say doping, I mean we're introducing some other kind of element into these metals or semiconductors. And is it going to increase the conductivity or is it going to decrease the conductivity? It's going to be different in these two cases, and hopefully we're going to try and figure out why that is. So let's think about the different factors that play into overall conductivity. And there are three terms to remember. First is this N term, how many? So this is referring to the number of free carriers in the system. How many charged particles are there that can move around? E is the electronic charge. Here we're going to talk about what is the charge on those particles. So if we're moving an electron around, or if we're moving around an ion that has a -2 charge, the ion would effectively convey twice as much electricity if it was able to move around the same amount. So that's the electronic charge of the free carrier. And finally, mu, the mobility. How easy is it for these carriers to move around? So if it's very easy, then I get a lot of motion and the overall conductivity can increase. Now I want to think about this in terms of an analogy. And we're going to think about a highway, right? We're going to think about how many people are able to move down that highway per unit time. So that's our conductivity in this case. So it's going to be a function of how many cars are on the highway, right? If we're in rush hour, we have a very large number of cars available. How many passengers per vehicle are there? If there's only one person in each vehicle, this would be, one. We could consider, if we want to move more people down that highway, we could consider increasing the density of passengers per vehicle. And finally, mu, the mobility. How easy is it for these cars to move? So in this traffic dense highway, the mobility is going to be what's going to control the overall conductivity, right? Think about if you're driving in LA or maybe in New Delhi during rush hour. In these cases, those cars are going to only inch along, right? The mobility of each vehicle is going to be very low. And that means the total number of passengers, the total number of people per time moving down that highway is also going to be small. Now think about maybe an hour later. I might still have a large number of cars on that vehicle, but the traffic is cleared up. So the mobility is now higher, they're able to move faster, and I get a much larger overall flow of people down that highway. Let's think about the other N member, right? Let's think about a highway that's relatively empty. So N is a very small number. In this case, the total number of people down the highway, there's not really any traffic to consider. So the mobility is probably going to be about the speed limit on whatever that highway is. If I want to increase the number of people flowing down that highway, I want to focus on N. I want to focus on putting more cars onto that highway. So I use this analogy because it's a very good description of the two N members, of the metal and the semiconductor case. So let's think about metals first. Metals, if you remember, I have enough electrons to partially fill an energy band. And so it's very easy to excite electrons up to higher unoccupied energy levels and allow them to conduct along. So that means N is very, very large. The number of free carriers in copper, in aluminum, in all these metals is a very large number. What limits the metals is this mobility. So if those electrons are able to travel relatively easily without scattering, they could have a high mobility and the conductivity, overall conductivity, could be high. If there's something that I introduce that's causing those those electrons to scatter and not flow very easily, then that could decrease the mobility, decreasing the overall conductivity. And when I talk about doping or conductivity in alloys, that's exactly what happens. So we're going to think about an example. Nichrome wire. This is a metal wire that's oftentimes used for resistive heating, and it's nice because we can control the resistivity very easily by controlling the percent of chromium in the system. So I see if I have a pure nickel wire, my resistivity is low. That means my conductivity is high. As I start increasing the percent of chromium in that, the resistivity increases dramatically. What am I doing? The number of free carriers does not change very much in this case. In metals, I have plenty of free carriers. That's not the limiting factor. The limiting factor in the metals is this mobility, that traffic density, right? So if I start thinking about a picture of pure nickel, and let's start introducing some chromium defects. You know, the electrons are moving along, they're flowing, but when they hit this defect, they're more likely to scatter. And that makes it more difficult for the electrons to flow through the system. The more chromium atoms I have in here, the more potential defects there are that will scatter electrons. So the result is, as I increase the chromium concentration, the overall resistivity increases. Now this is kind of weird, because if I thought about a system where I go all the way from pure nickel to pure chromium, these are both metals, and so their overall resistivity of pure nickel is quite low, and the resistivity of pure chromium is also quite low. But once I start alloying it, I increase that resistivity dramatically. So I can't say that the resistivity of nichrome is an average of the resistivity of nickel and the resistivity of chromium. It doesn't work that way because of this atomic mechanism. When I'm increasing the concentration of chrome in the nickel lattice, it's soluble within that nickel, so those atoms are going to be dispersed relatively evenly, and they're all going to be creating scattering sites. So I have to think about it on this atomic level, not this bulk mixing level. Semiconductors. The semiconductor case is this empty highway case. Semiconductors are largely not limited by the mobility. I can have some semiconductors that have a higher mobility than others, but the biggest thing that's going to impact the overall conductivity is if I increase the number of cars on that highway, the number of free carriers. So again, remember the semiconductor picture. Here I could have my valence band, and here I have my conduction band. The valence band is going to be full, and the conduction band is relatively empty. So I can increase the number of carriers in that conduction band by one of two ways. I could increase the temperature, excite more up there, or I could put dopants in. And so dopants are elements that have electrons that are very close in energy level to the conduction band, so it's easy for them to hop up there. Or maybe they're acceptors, so they have available energy levels very close to this valence band, so it's easy to excite an electron up there. In either case, in the silicon, we're not as focused on that mobility term. The biggest impact is that number of free carriers. And so if I look at a plot of resistivity by the concentration of acceptors or donors, so two different types of dopants that I could use, I find that the resistivity drops as I increase the number of these dopants. And in fact, early on, it's about a 1-to-1 ratio. So for each dopant, so if I increase the dopants by 1 order of magnitude, so from here to here, I decrease the resistivity by almost 1 order of magnitude. It's a little bit less. And it's less because there is some impact on the mobility. You know, again, I'm introducing defects, and they are, they are providing scattering sites. The biggest thing is that the number of dopants that I'm talking about is much less than in that metal alloying case. So 10 to the 15th per centimeter cubed is still part per million type range, rather than 1 to 10%, like in that nichrome wire example. Okay, so in summary, the resistivity is going to increase in metals with the concentration of dopants, and that's because those dopants are scattering the free carriers and is decreasing the overall mobility, which decreases the conductivity, increases the resistivity. On the other hand, in semiconductors, the resistivity is going to decrease with the concentration of dopants. And in this case, it's because largely we're changing N. We're changing the number of carriers, and we're having a much bigger impact on N than we are on the mobility in the system.